On about this time, I start to drag on the day. You guys feel the same way? Got a lab that starts at 9. Whew, it's a full day for me. Anyways, yeah, poor teacher. It's much easier being on this side than a student. At least I think it is. Depends. All right, so we're starting back up again today. Couple announcements. So just for scheduling, we're going to get done with Chapter 4 today. I mean, in like 15 or 20 minutes probably. And then we're going to move to Chapter 5. The test is a week from Wednesday, and it's not going to cover Chapter 5. So only the oxidation stuff, which we're ending up now, will be on the test, besides the stuff that we've talked about since the beginning of the semester. That will also be on the test, but the gas law stuff will not be on this test, it'll be on the next one. So Monday, I'm going to do a review. I'm basically going to go over the old exam, so a previous exam that I had, and I have it posted on Alima, so I will go over that in class as well. So the midterm, so next Wednesday, it's going to be 20 questions, multiple choice. Not just, it's going to be very similar to the previous midterm, at least in look and style. The difference, though, it's going to be multiple choice, plus you can show your work for partial credit. So I'll do a little bit of both. So does anybody have any questions? Well, you can ask questions again later, of course, but do you have any questions right now? Yes, please. I will provide you with all the equations you need. So you'll get the equations, you'll get constants. You don't have to memorize them, and you get a periodic table. I don't typically release that before class because there's always 1 or 2 students that take that and then add extra stuff on it. And so just so you know, you will have everything you need. And if you need more, like if you don't remember milli means 1,000th, I'll tell you milli means 1,000th. So all you have to do is ask. Other questions? Okay. So this is where we left off. Talking about oxidation states. And this is just a way to keep track of electrons. So, man, how many people are 2, 4, 6, 8, 10? And there's like half the students didn't show up. All right. Well, you guys are paying to be here. You don't want to show up. All right. Okay, so here are the rules. Oxidation state of a free atom or an element is 0. So oxidation state of the monatomic ion is its charge. Sum of oxidation states for a neutral molecule formula unit 0. For an ion is its charge. Alkalis have +1 in compounds. Alkyl earths have +2. And then this handy dandy chart. This is another thing. There will be oxidation states on the test. You will get this chart. You'll get solubility rules too. I'm very much against memorization. I'd rather if you focus on how to do the problems now. Now the caveat for that is if you go and take some of the tests like the MCAT and whatnot, they make you memorize this. But I'd rather if you focused your energies on learning the process now and then worry about the flashcards if you decide to take one of the more advanced classes or more advanced tests. Okay, and we covered this last time. I just want to do a quick review. Assign oxidation states. That's free element, 0 oxidation state, monatomic ion, +1 charge. So for potassium and fluorine, the sum of those equals 0. Potassium is an alkali, it's +1. That forces fluorine to be -1. Not surprisingly though, because fluorine tends to be -1. Carbon dioxide, carbon plus 2 oxygens. The 2 oxygens come from the 2 under the CO2. Carbon plus 2 times oxidation number of oxygens equals 0. Oxygen tends to be -2, forcing carbon to be +4. Sulfate here, unlike carbon dioxide, was equal to 0. The sum of them were equal to -2, the charge of the ion. And then oxygen be -2 forces sulfur to be +6. Here, potassium peroxide, 2 potassiums plus 2 oxygens equals 0. Alkalis have to be +1. That forces oxygen to be -1. And the name peroxide means oxygen in the -1 state. So that's where we left off. Everybody see this? Any other questions? Okay, so I'm going to continue with another example. Oxidation states in potassium dichromate. So 2 times potassium plus 2 times chromium plus 7 times oxygen is 0. And that's just the number of the atoms, and we're going to assign each the oxidation state. Potassium tends to be +1, oxygen tends to be -2, so I'm just going to go ahead and put those there. +1, -2, I'll put the +1. Chromium now, the question is what to do about chromium. 2 times 1 plus 2 chromiums plus 7 times -2 equals 0. This is then 2, this is -14, so 2 chromium -12 equals 0. Then that means chromium is 6, +6. Now, chromium being in the +6 state actually is very dangerous. So if you've ever seen the movie, read the book, Aaron Brockovich, and talk about the cancer that they got from exposure to this stuff, this is what it was. It was chromium in the +6. Chromium in the +6 state is very bad. It gives you a skin rash. I don't like the stuff because A of all, it gives you a skin rash, and B of all, it can give you cancer. So it doesn't mean one exposure will give you cancer. We used not dichromate, but we used chromate in the chem lab today. Turned all the well plates yellow, if you notice that. Yeah, that really that kind of minion yellow color. So, which also, if you ever go to like old art, like if you see a bronze statue and it's yellow, you probably don't want to touch it because it's probably dichromate that's on it. It turns it's a really yellow. If you hear the word patina, that's what makes sculptures color. It's a very bright yellow color. But so chromium +6 is very dangerous, but chromium metal, not so bad. Chromium +3 is completely fine. You can, like, they put it in glass. So there's chromium glass that they use for frequently for like ovens and stuff. You can eat it on it. It's fine. The +3 state is totally fine. +6, rip 3 electrons off, then you get cancer and a rash. So it's the oxidation states very much change the chemistry of what it is you're working with. And I think I mentioned last class talking about sulfur. Sulfur in the -2 state, man, we can smell that stuff. We can smell sulfur in the -2 state down to the parts per trillion. But like sulfur, like plain old sulfur, it's like sulfur. It stinks, right? The yellow rock, it stinks, but it's not like instant death, right? If you smell sulfur, you're like, oh, this sulfur doesn't taste. This smells very good. You can touch it in your hands. Hydrogen sulfide, that stuff smells like rotten eggs. You're like, oh, get me out of here, really fast. So the smell is much stronger in the -2 for at least for us as humans. Okay, so let's see if you follow it. What is the oxidation number in manganese and potassium permanganate? And I'll give you a hint. Potassium is +1, oxygen is -2. So I think it's A0, I think B7, All right, most of the class is going for 7. We got. Are you? That's the right answer. So, a couple people aren't playing. So +1 plus manganese plus 4 times -2 equals 0. 4 times -2 is -8. Bring it on both sides. Well, +1 minus 8 is -7. That means manganese is 7. So, questions with how to do this? Okay, so you saw last class accidentally that I watch Ancient Aliens. You ever seen the show Naked and Afraid? They let you in that show. They take people and they put them out in the woods, and they let them take 2 things. One of the people took potassium permanganate, was the item that she took, and it can be used to purify water. The other thing that's nice about it, it's a very good, it's antifungal agent. They used to put this on people's feet for for trench foot in World War I. If you have a very serious fungal infection on your foot, they'll put potassium permanganate on you. It's a good way for that. It's purple. It's purple stuff. It turns everything purple. And they had a solution in the show. They had the solution of potassium permanganate. But that's another one of my stupid guilty pleasures, I guess. I don't watch much TV. Just the good stuff, of course. Okay, so now we're going to talk about oxidation reduction reactions. So if you recall, oxidation means loss of electrons. So if it's oxidized, it's losing electrons. Reduction means gaining electrons. So if you look at this equation here, we have magnesium metal plus water makes magnesium hydroxide and hydrogen gas. So if you look at the oxidation states, they're all in red here. Magnesium is a free element, it's 0. Hydrogen +1, oxygen -2 in water. Magnesium now goes to +2. It's an alkaline earth. It's a compound, so that's +2. Oxygen still -2, hydrogen +1. Now hydrogen gas, it's a free element. It has then the oxidation state is 0. Now, if you look at what's going on, magnesium is being oxidized. It's going from 0 at oxidation state, meaning all of its electrons are accounted for, to +2, meaning it's missing 2. Hydrogen is going from +1, meaning it's missing 1, to the 0 state, so hydrogen in this reaction gains an electron. And since magnesium is being oxidized, we say that it's the reducing agent. It causes the reduction. So I think of like James Bond. If you like James Bond is the deliverer of death. He's the license to kill. So does James Bond ever die, though? Like, not in the movies. He's always the one doing the killing, right? So magnesium is delivering the reduction. How is it delivering the reduction? By being oxidized. Oxidized means that electrons are ripped off, and reduction means accepting electrons. So by the fact that magnesium is providing electrons to something, by being oxidized, it is allowing the reducing to happen. It's a reducing agent. Likewise, water here is the oxidizing agent because it's grabbing electrons. So it's grabbing electrons, which is causing the oxidation. It itself is being reduced, but in the act of grabbing the electrons, we say it's the oxidizing agent. I know it's like opposite, right? But students seem to have a little bit of trouble with the logic. Does anybody want to guess what the most common oxidizing agent is? At least here on Earth. What's the most common oxidizing agent? Anyone want to guess? It's not water. It's in the air. Think. Oxygen, yes. Oxygen is the most common oxidizing agent. You never would have guessed. Anybody want to guess what the most common reducing agents are? It's not magnesium. No, not typically, at least. Unless you have a food fight. It's, yeah, fuels are the most common reducing agents.
So either like, natural gas, oil, gasoline, or for us, sugars. Right, so reducing agents. Fuel is the most common one.
Right, fuel plus oxygen makes fire. And that's what I said there. What is oxidizing? What is oxidized is a reducing agent, and what is reduced is oxidizing agent. So we have this equation here. Unbalanced oxidation of glucose. What's the reducing agent? How about I give you the oxidation states? 0 plus 1 minus 2, 0 plus minus 2 plus 4, 0. It depends. You could logic your way through this as well, which we'll talk about. So how many think the reducing agent is glucose? How many think it's oxygen? Okay, it's one of those two. These are products, and they're not, so people aren't getting it. It's not water or CO2. They're on the wrong side of the equation. Reducing agents and oxidizing agents are always on the left reactant side. So, what's being oxidized? Which one of those is being oxidized? Yep, it's being oxidized because the carbon goes from 0 to plus 4. So that means it's losing 4 electrons. So it's being oxidized. So then does that make it a reducing agent? Yes, it does. What did I say was the most common reducing agent? Yep. And what's the most common oxidizing agent?
Don't worry, the noon class didn't get either. So, and I even said the oxidation of glucose. You're literally adding oxygen. Remember, a definition of oxidation was adding oxygen. You are literally adding oxygen to this, plus O2, adding oxygen. So you could logic your way through that by the fact that you're adding oxygen to it. So then this is oxidized, which means it's the reducing agent. It delivers the reduction. So, but if you look at what method never fails is looking at the oxidation states, and carbon goes from 0 to plus 4. Therefore, it's being oxidized. Reducing agents, they deliver electrons. What is oxidized is the reducing agent. Yeah. The oxidizing agents deliver oxidation. So they accept electrons. Oxygen takes electrons. It's the oxidizing agent. Other questions? No, it's like opposite. It's like, another example I say is like if someone is a womanizer, or let's say a male, I guess in heteronormality, if a male is a womanizer, the person's not a woman, it's a womanizer, it goes after the women kind of thing. Just like the reducing agent is in fact oxidized. It's the opposite of what it says it kind of is. So I know it's kind of backwards logic. Making sense? Hopefully? Okay.
All right. So we are now at the end of what is going to be on the first midterm. So this stuff, albeit its importance, it's not going to be covered on the first midterm. This will be on the second midterm. So don't completely shut your brains down, but don't study it so intensely that you're going to push room out of your brains for the other stuff. Yet. Okay. So chapter 5 is all about gases. So we're going to get into gas laws. And let's say I want to snorkel down, and let's say I don't want to get scuba certified. You know what? I can snorkel. Why don't I just have this really, really super long snorkel, and I can go 100 feet underwater. I have a 105-foot snorkel, so I'm going to snorkel down 100 feet underwater. Will this work? Why not? What if I get bigger lungs? What if I'm I transfigure into Harry Potter, transfigure into a blue whale, and I put a 100-foot snorkel on my blowhole, and I try and breathe as a blue whale underwater? Pressure would be too much. So it turns out that the atmosphere, the average pressure of the atmosphere on Earth at sea level is equivalent to about 33 feet of water. So 100 feet of water, this is approximately 3 atmospheres of pressure. So we have an atmosphere of pressure here, then another 3 atmospheres of pressure here. So the whatever lungs are down here, they feel a force of 4 atmospheres. So the air inside of whatever lung creature is there has 4 atmospheres, and up here, this gas pressure is 1 atmosphere. So what would happen to someone if he or she tried to breathe in this scenario? Lungs would collapse. So why is that? It's because we don't cover many engineering concepts in the textbook. I do in lecture, but flow happens for 3 reasons. Number 1, and probably one of the more common ones that we use, is from high pressure to low pressure. So things will always flow from high pressure to low pressure. And one of that is simply just pouring things out. So because of gravity, if I have this shut, but if I open this up, the water will pour out because of the weight of the water pushing down. There's higher pressure up here than there is down here, so water will flow downhill, not surprisingly. And that works for gases too. So when you have your compressed gas cylinder or something like your propane tank, it's under pressure, you open up the propane tank and the gas flows from the tank to your grill. So from high pressure to low pressure. And also things flow from high temperature to low temperature. So if you put your ice cream in the oven, you turn the oven on, the heat goes from the oven and melts the ice cream. The heat doesn't leave the ice cream and become colder, and you get a frozen block of ice cream in your hot oven. No, it doesn't work that way. Heat always goes from high temperature to low temperature. The last one is high concentration to low concentration. If I open up a bottle of perfume and leave the room, come back, the room is full of perfume. I can't have a room full of perfume. I leave a bottle, come back a couple hours later, perfume is all back in the bottle. No, it doesn't work that way. Always goes from high concentration to low concentration. So here, this wouldn't work because the higher pressure air in the lungs would be pushed out due to the pressure differential. And so what is pressure? Definition of pressure is force divided by area. I should write this out. Force divided by area. So a force like a PSI, this is a pound per square inch. So it's pound is a force. So, and we talked about that between mass and weight. So weight is a force. So weight specifically is your mass times the gravitational pull. But I was reading, not every one of you are in my lab class, but we talked about this in lab.
and your weight can actually change here on Earth. If you go up and down in an elevator, you ever that sinking feeling in your stomach? You're going up and you're like, oh, I feel heavier. And you're like, then you go back down, you get that, whoa, I feel like that felt weird. You actually are less, you have less weight. And well, at least if you were standing on a scale, the scale would show you to have less weight. I guess you could argue one way that that you still have the same amount of weight, even in space. You still have your gravity is still pulling your center of mass towards the center of the Earth, so you still have weight in that regards, but you feel weightless. But if you are doing things like if you're falling here on Earth, your weight will change. Also, in the elevator, the normal force, the force pushing up from the elevator, would go down, so preventing you from falling. So your weight can change. Okay, but anyways, pressure is force per area. We use PSI quite a bit, pound per square inch. And an atmosphere of pressure, so atmosphere equivalent of the Earth at sea level, it's 14.7 PSI. So about 15. You get that number if you want. So you're writing it down. Go ahead and write it down if you want. And I told you also that that 33 feet of water is equal to an atmosphere. So so a calculation that firefighters and engineers use really frequently is that 33 feet of water is equal to 15 psi of water pressure. So if you're a firefighter and you need to shoot water 100 feet up, so water is very frequently used to put out fires. Another surprising thing you learned today in chemistry class. And yeah, blind equals blown. So let's say I need to shoot water 100 feet up in the air. How do I do that? Well, they turn the fire trucks, among other things, they're big pumps. So they put they hook a hose up to the fire hydrant, and they're pumps. And they have ladders and they have pumps, basically, of what a fire truck is, and sirens, of course. So to shoot water up 100 feet in the air, they would need 45 psi of pressure in the hose to do that. And likewise, if you have a high-rise building and you want water to go up to the bathrooms on the top floor, you can do calculations to how much water pressure you need to have in your pipes for the water to make it up to the top of the building. And what they use is 33 feet is 15 psi. And I know it's 14.7, but that 0.3 psi, they consider that to be like negligible error. There's a lot of error involved in calculations, like in engineering. And engineering, if you study more of it, you just kind of wing things. So, what's that? There's something called a safety factor. You would feel pretty safe about your house. So, when you get materials, have you studied stress and strain yet, though? No. Oh, no. Okay. So, there's a safety factor. It's usually about 2. They pretty much over-design houses, buildings to a great degree. Okay, so and part of what they put in there is a safety factor, and then certain materials are allowed to have a certain amount of weight, and they're very conservatively generated. So, and it's actually in part we have the Canadians to thank for that. They had a bridge that fell apart because of faulty engineering, so they created something called the Order of the Engineer. I don't have my ring. I have it, but it's at home. I don't wear it very much. It's an iron ring. The one I got is steel. They ran out of iron from the bridge. They took the iron from the bridge and they made rings from it. And then if you promise to be an ethical engineer, they give you a ring. But they've run out of the iron from the bridge, so they give people. You can choose to get iron, but I chose steel. So I have a steel. You're supposed to wear it on your pinky finger. And well, I wear it on my left hand. You're supposed to use it on the pinky of your dominant hand, but I'm ambidextrous, so I just like it on my left hand better. But anyways, yeah, don't worry about your house. It's pretty, unless it's old. Okay, the safety factor is pretty solid. I mean, you don't see structures falling down very frequently, at least not in the United States and Canada. Okay, but But anyways, pressure is force per area. Another thing that is pressure is sound. A sound wave is a pressure wave. Sound wave is also a specific type of wave called a longitudinal wave. So you're probably more familiar with what's called a transverse wave. We'll talk about that when we get to light. Light is a transverse wave. Ocean waves are transverse waves. So a transverse wave is that the motion is perpendicular to the direction of the wave. An ocean wave moves this way, but if you're in the ocean, you go up and down. Your motion is perpendicular to the direction that the wave is going. That's a transverse wave. Sound wave is a longitudinal wave. The displacement of the air is the same direction that the wave is going. So that's the longitudinal wave. It's parallel. The displacement is parallel to the direction of the wave. And the sound comes in our ears, right? So the sound we can pick it up with our eardrums, and then it goes. I'm so bad at biology. Whatever the three bones, and it's like the anvil, the sickle, and something else, or I don't know. That those vibrate from the eardrum, and that carries a signal up through the hairs feel the vibration, and that goes to your brain or something like that. I think that's how your hearing works. But either way, sound is a pressure. It's a pressure longitudinal wave, and like big explosions, sometimes you can feel it in your chest. Like if you see fireworks, you can feel the pounding in your chest. Actually, some of the sound we can't hear, they're called, like the two really low ones are infrasonic. And you can feel those, at least I can feel them in my feet. Like if you ever feel construction and something's hammering, and I can feel the vibrations coming from the ground in my feet sometimes. So that's only if I'm around. I don't feel it all the time. That's only if I'm around where they have a building being built. But okay, so all right. So now that we've learned a little more pressure, and let's talk a little bit more about the gas laws. So now I'm not going to go through all the gas laws. I'm more interested in the ideal gas law, which I'm building up to. But let me start by talking about Boyle's law, and we're going to have a lab on this. So this is a scientific law, meaning a summary of observation. So many experiments were done, and I think it was Professor Boyle, whatever, doctor probably writes, but Boyle did lots of experiments and figured out that pressure is inversely proportional to the volume. So this is what this alpha symbol, it looks like a fish. It means proportion. That means pressure is in proportion to 1 over volume, also known as inverse proportion. And I remember in high school chemistry, they presented Boyle's law this way: P1 V1 equals P2 V2. What that means is when one goes up, the other one goes down. So that means if I have a piston and I have gas in there, if I apply pressure, if I push on the piston, the volume goes down. And then if I take it off, the gas expands, so the volume goes up. That means the pressure goes down. It's kind of like, also a colloquial example would be like my bank account balance versus how much fun I'm having. So if I'm having lots of fun, I'm going to go out and enjoy myself, travel, these kind of things. That costs money. My bank account balance goes down. So let's say, for instance, though, I'm like, well, you know what? I need some money, so I'm going to watch lots more Netflix and eat crock-pot dinners, and my bank account balance goes back up. Right? So that's the inverse proportion. Then there's Charles' law, where volume is directly proportional to the temperature. So that means that if the volume goes up, temperature goes up, or volume goes down, temperature goes down. So they go together, whereas pressure volume is opposite. And Charles' law, the classical example for that, is a hot air balloon. So we don't have them here in Hawaii, but the way they work, you have a droopy balloon, and then you hit a flame underneath it, and after you do that, you get a big hot air balloon that then can float. So
I remember as a kid we used to like hot air balloons. We used to run after them, say that's so cool. I've never been in one, and quite frankly, I don't want to. What was that? I'm afraid of heights. Just a wicker basket and death. I don't know. I guess maybe if you blindfold me, I'll be happy. No, Mike, we're still in the parking lot. Don't worry. All right, so hot air balloon. And the other thing with, now we're using temperature. When you work with temperatures with ideal gases or gases, you have to use a different scale. You have to use Kelvin. So, and you remember, so Kelvin, here's Kelvin. It's after Lord Kelvin. So if you two are a scientist and a lord, maybe you'll have stuff named after you too. But Kelvin is equal to degrees Celsius plus 273.15. So notice a couple things. First of all, there's no degree sign in front of Kelvin. And the reason for that is that Celsius is a relative scale. So relative scales have the degree sign up next to them. So Celsius is relative to water, right? So water at 1 atmosphere of pressure will melt at 0 degrees and boil at 100 degrees. So we also call Celsius sometimes centigrade because it's 100 unit steps. Kelvin is the absolute zero form. It's the absolute temperature form of Celsius. So do you remember when I talked about the definition of temperature, what it is? Do you remember what I said in the beginning of the semester? Temperature is, yes, average translational kinetic energy. So do you remember, so translationally, I can move this way. I'm moving very translationally. How else can I move? I can rotate, and I can vibrate. Right, so molecules do that. So if this is a water molecule, it doesn't just move around like this. It rocks, it rotates, it vibrates, it dances around. So water does that, it dances around everywhere. Now temperature specifically is this motion. It's the translational motion. Okay, so that's temperature. And absolute zero is when it's not moving. So when translational motion stops, it's at absolute zero. Even at absolute zero, they still rotate and they still vibrate. So there's still motion going on. It just doesn't go anywhere though. It doesn't move around. So that's what absolute zero is. That's why you can't go below absolute zero, because you can't go any slower than not moving. Right? So I remember I was a judge for a science fair, and this student was talking about cooling things down. It says, and if I did this, it would get down to negative 10,000 degrees. I'm like, I think that's not really that possible. So I mean, it was a kid, and it was, he was doing an experiment. He was very proud of it, of course, and it was a good method, but can't get colder than not moving, right? Can't break that absolute zero. What's that? I know. I destroy little kids' dreams too. Don't worry. There's another unit. R is degrees Fahrenheit, and I think it's about 450-ish. Talking this in the last class. I can ask Siri. What's absolute zero in degrees Fahrenheit?
It's minus 459.7 degrees Fahrenheit.
Okay, there we go. 450. So you might see this if you see a temperature and it's in R, you're like, what is this? Like a pirate? R, it's pirate temperature. No, it's the absolute form of Fahrenheit. So absolute zero is about minus 450 Fahrenheit. But that's not in this class. They use it in some engineering applications. So engineering, it's only also in America. They don't do it anywhere else. But I guess maybe Britain, because they have the British thermal units. They do a little bit of BTUs there. But I don't know. I've never talked to a British engineer. But okay, so with this in mind, though, let's see if you're following. What is negative 100 degrees Celsius in Kelvin? course, the equation's right here. I think it's A173. All right, everyone's going to that. Okay, good. All right. Your brains are working. Nice. Okay, like I said, I'm not going to cover all the laws, but let me cover Avogadro's law. There's also Gay-Lussac's law as well, but Avogadro's law is volume is directly proportional to the number of moles. So how do you blow up a balloon? You add more air to it, and when you add more air to it, it increases the number of moles, and what happens to the balloon as you add more air to it? It gets bigger. Yep. So volume is directly proportional to number of moles, which is why you blow air into balloons to blow them up. And but you never thought about that when you were blowing up balloons when you were a kid, right? Now, I am now verifying Avogadro's law. What you should have thought. Okay, and then last thing we'll talk about is the ideal gas law, and this combines the other gas laws together. And this is PV equals nRT, so pressure times volume equals N the number of moles times R the gas law constant times the temperature. So, and what is R? R is actually two different constants. R is actually Avogadro's number times what's known as the Boltzmann constant. So the Boltzmann constant deals with probability and distributions and statistics on a grand scale. So this equation is completely mathematically derived. So it has no meaning whatsoever. This was not experimentally determined. This is a complete, perfect mathematical model. So kind of like if you think of what's the most perfect person, what's the most beautiful person you could ever have. I think there's some woman in France that's considered to be the most beautiful person or something like that. They have a TV show about her or something, or at least I saw an article on the stupid stuff I look on Facebook and stuff. Right, so this person is the most beautiful woman. So what is the perfect part of beauty? Well, this is the perfect gas. The ideal gas follows this, and an ideal gas is, we're only going to deal with ideal gases in this class. We will talk about real gases. Real gases. You will not be tested on real gases. And the method that this book deals with real gases is really bad, actually. It uses something called the van der Waals equation. The van der Waals equation is not a very good way to go. There's better ways to do it. So the ideal gas, and we'll talk about it a little more when we get to kinetic molecular theory. The ideal gas is one where the particles themselves have no volume, but the gas has a volume, but the particles have no volume. And it's also, the gas has no attraction for each other. So why does that matter? Well, if you have two particles and they have an attraction for each other, they will hang around together, and now those two particles will act more like one particle. So, and that will effectively have the pressure and or volume of that. So it's going to change this term to, it'll decrease this side of the equation for the attractiveness, the stickiness of the particles. And all particles have attraction for each other. Helium is the best ideal gas, but even that has a little bit of attraction for itself. And then the volume, if you have really low volume and or really high pressure, I mean the gas gets really tight, but then the particles themselves, the atoms and molecules, now the fact that has a volume, that skews the volume here. You have a little bit extra volume than you would expect from that. So ideal gases, they work pretty well under low pressure and high temperature. So right now, 1 atmosphere of pressure, 298 Kelvin that we're at right now, this is considered to be low pressure, high temperature. Low temperature is like minus 100 degrees Celsius. That's low. That's low temperature. High pressure is like 100 atmospheres. So like if you're on Venus, the surface of Venus, that's high pressure. So Mars and the Earth would work well for ideal gas law. So we're
we're pretty good there. Mercury would even be better. It has a very high temperature, very low pressure. So, and even at this temperature and pressure, there's still error associated with the ideal gas. So, ideal gas law, there will be, depending on the temperature and pressure, there'll be about like a 2 to 5-ish% error of that. Of course, the book doesn't talk about that, but I'm just kind of telling you so that depending on what relationship you use, you can actually get error from that, and the ideal gas law will have error. And I also think it's interesting. I mentioned about human beauty. Human beauty it changes. So right now the most beautiful form that we consider is a late teens female. So late teens female is considered to be the most beautiful. But if you look back into the time of the Renaissance, the most beautiful form was the 18-year-old male. So like if you look at Michelangelo's David, he's like a ripped 18-year-old male. And if you look at some of Michelangelo's other stuff, like the Michelangelo, the painter and sculptor, like I like art. So, but like the Sistine Chapel, if you look at females, like the women up there, they're basically ripped 18-year-old guys with breasts. So that was considered beautiful, is to be a skinny, ripped 18-year-old male. And so then the women were kind of portrayed that way in the art. And Moses, Michelangelo did a sculpture of Moses, basically a ripped 18-year-old male with a beard and horns on his head. Horns were from a mistranslation of the Bible. So, but that was considered beauty back then. Now we have a different version of beauty, and this is also a model. So this is an empirical. No, it's a derived model. So ideal gas law is a complete mathematical model. And when I hear the word model, I think about Victoria's Secret models, partially because I used to work there. I worked at Bath & Body Works in Victoria's Secret. It's a company called Intimate Brands. It's part of Limited Corporation. And like the models there, they don't look like they do in the photographs. They first of all, when they have the photographs done, they cake them up with war paint, with makeup. And they do the lighting so, and then they airbrush the heck out of it. So I mean, that's not real women that you see in the catalogs. It's complete like computer imaged enhanced artwork of sorts, functional art, I guess. So that's the same idea with the ideal gas law, although the Victoria's Secret models are in fact women. I mean, I've never met one, but I mean, you could meet one. But the ideal gas law, it's a complete idealized, like semi-artistic, like a Michelangelo sculpture idea of a gas. But it works very well, at least at this temperature and pressure. Like I said, the error is on the order of less than 5% or less. And depending on your application, we talked to, like, if you're worried about your house, I mean, having the safety factor of your house. I keep on talking about error. Management of error is an issue for science and engineering. And there's error in many places you wouldn't expect, like the equation E equals mc squared. That's not exact. There's actually lots of terms that are neglected in that. So this is not an exact, it works very well, but it's not an exact relationship. There are terms that are discounted, and it depends on the application. You can have to change the equation. So I had a student in the previous lecture, she was asking me all about this, because I frequently, I truncate my answers, if you notice that. Instead of like, for carbon, I don't put 12.011, I put 12. Hydrogen, I put 1.008, I just say 1 per gram per mole for hydrogen. And so I just truncate the results. I just truncate my calculations, and then I get an answer sometimes that's like 2 decimal places off from the book or something like that. And they're like, what about this? I'm like, well, that's just truncation error. I'm like, what? How do I know when I can truncate and when I can't? I was like, well, it depends on your application. So has anyone ever heard of the Deep Impact Probe for the comet that NASA did? This was like 10, 15 years ago. This was a cool experiment. So there was NASA launched a probe up into space, and it shot a projectile towards a comet,
and it actually struck the comet. So they wanted to see what's inside the comet. So they found out much about information about comets from this. So they had this up in space. They had a spacecraft, and then it shot a projectile that hit a comet, and it worked. It hit the comet and it cracked the surface of it. And but can you imagine the calculations that they had to do for that? I mean, it was probably going on the order of like 100 million miles. They shot the thing, or maybe it was merely 20 million. I don't know, because I mean the distance between the Earth and the Sun is 93 million miles. So I mean it's probably on the order of 100 million, 20 million thereabouts. And the comet's moving too, right? I mean you're using a part of a bullet to hit another bullet. You're using a bullet to shoot a smaller bullet, another bullet flying by. And can you imagine the calculations? I mean, they probably had to include the gravitational pull of Jupiter and the moon and the Earth and that kind of thing in that calculation to be able to hit the comet. Because if they're off by like a really small amount, like a nanometer, but over 20 million miles, they're going to miss it by like 50 meters. So if you're doing that kind of calculation, you have to have a super big number of figures. But if you're just doing something like here, when I have minus 100 degrees Celsius in Kelvin, you can get rid of the 0.15. I mean, you can get, depending on your application, you can truncate your results. So if you see me truncate, it's all part of the, I guess, managing of error, and it's part of the, I guess, I don't want to say sloppiness, it's just what is typically done in sciences and engineering. And if you study it more and more, you'll see that quite a bit. And we'll talk about that. I'll talk about a few things more when we get to thermodynamics. Okay, so ideal gas law, calculate the volume occupied by 0.845 moles. Doesn't matter what the gas is, some ideal gas at a pressure of 1.37 atmospheres, temperature of 315 Kelvin. So the way you do this, so PV equals nRT. So this is the ideal gas law equation. And we want the volume, sulfur volume, nRT over P. So part of you being here, I assume that you know how to do this. So the way that you can do this, you can multiply both sides by 1 over P, like that. Or I kind of see it this way, like, whoop. I just kind of rearrange that in my head just like this. So if you have trouble doing stuff like this, solving for these, this is when you should get a tutor and or see me, and we can work on some of the stuff. But solve that equation for volume. Now you just put it in. The volume, so number of moles, 0.845 moles times R, 0.08206. Liter atmosphere, mole Kelvin, temperature 315 Kelvin, all over, what is the pressure, 1.37. 1.37 atmospheres. Now let's talk about the units. So we have this mole and this mole, right? This mole's on the one on the left is on the top, then divided by the moles, that cancels. The kelvins cancel here. The atmospheres cancel there. And so the unit that we're left with is liter. And then we just put this in our calculator. Oh, do I? Okay. That better? R is a gas law constant. So, and you get the constants, you don't have to memorize them. And this is 15.9 liters. And picture. There, like that. Okay. So recap for this one. What's the volume occupied by that number of moles of ideal gas at that pressure and that temperature? So we take the ideal gas law equation, solve for volume, input the numbers, and then we get the 16 liters from that. Questions here on how to do this? Okay. Our pressure is 0.5 atmospheres, volume 50 liters, temperature 50 Celsius. What are the number of moles in this? All right, so I'm going to think it's A, half a mole. I'm going to think B, 1 mole. I'm going to think C, 3 moles. I'm going to think D, 6 moles. Ooh, we got a, oh, you guys fell for the trap. You underestimate the sneakiness. So it's number of moles is PV over RT. This one here is 50 Celsius plus 273. This is just 50 Celsius. So when you do the ideal gas laws, you have to use the Kelvin temperature. So it's B there, because this one down there, that answer, the 6 moles, is by using Celsius instead of Kelvin. So, you fell for it. So don't ever fall for it again. Question?
N is always in moles?
Yes. Yeah. P is pressure, V is volume, N is moles, R is the gas law constant, T is temperature. So now one thing, which just when I'm thought you got, I'm going to confuse you further. The units Celsius and Kelvin mean the same thing. So the magnitude is different. The units are the same. So if you multiply and divide, and also change of. So meaning if you have a change of 25 degrees Celsius, you have a change of 25 Kelvin. And if you multiply a term by a Kelvin, it's the same thing as multiplying and or dividing by Celsius. So, and that's more important when we get to next chapter, chapter 6, when we talk about thermochemistry, because frequently when you look at things like heat capacities, they'll give you the answer in Kelvin. It'd be like grams per mole Kelvin or something like that. And sometimes students are like, does that mean I have to convert to Kelvin? I'm like, no, if your change in Celsius is the same thing as a change in Kelvin. So you don't have to always convert. So converting will always save you if you want, but there are times that you don't have to convert if you don't want to. Save you a step. You get the same result. You get the same result if you convert it. But like I said, change of 20 degrees Celsius is the same as change in 20 kelvins. Okay. Although not everyone played in this, does anybody have any questions with how to do this? Usually it's pretty straightforward. Guess I should have gone around. Okay. Now we're going to talk about derivations. Okay. We're going to derive something, and I don't like deriving things, but I will for you guys. So we start with the ideal gas law, and we're rearranging it to this here. So we can take this and we can move the pressure over there and the number of moles over. Wait a second. Oh. And we can flip this. Now we can take this and we can flip it and we get this. It's probably a bad way to do it. How should I have done it? I should have done it this way. Let me go back. I should have taken this and moved this over here in the whole R. And then move the N over B there like that. Okay. That's a better way to do it. So do it that way. And what is N over V? This is moles per liter, which is the same thing as molarity. Okay, so capital M, that's moles per liter. And we can then multiply both sides by grams per mole. So let me show you this. So we have M equals pressure over RT. So that's what we just showed up there. And we can multiply both sides by grams per mole. So grams per mole is molar mass. So times molar mass there. I'm just going to, as my calligraphy M there is molar mass. And then this moles per liter, which is this, we multiply it by grams per mole. The moles cancel, and we're left with grams per liter. So density in grams per liter, this equals, over here, pressure times the molecular weight all over RT. So what I just showed you there is a derivation. You don't have to do it in this class. So many science classes, you will go through many, many derivations. You are not responsible for any of them. But that's among other things, this is kind of considered also a proof. if you can derive it, at proving something. So, okay, so I've proved that equation. And before I go on, let me include a few more things. So I told you an atmosphere was 33 feet of water, 14.7 psi. 10 meters of water is about 33 feet of water as well. So 10 meters and 33 feet, the same thing. The SI unit for pressure is kilopascals. So 1 atmosphere pressure is 101.3 kilopascal. A pascal is a Newton force per square meter. Square meter is this big. A Newton is a really wimpy force. You hit me with a Newton, that's nothing. A Newton is a wimpy force. It's the force. It's kilogram. Newton is a kilogram meter per second squared. So it's a very it's a pretty wimpy force. I'll just put it at that. Pound is it's not that much greater, but pound is a bigger force than a Newton. And it takes 101,300 kilopascals equal to an atmosphere. So you can see it's a pretty big number. Versus a pound per square inch, it's 14.7 pound per square inch. So that's of course a square inch is much smaller. A square inch is about this big, and a square meter is this big. So, but that's why PSI is such a smaller number, right? 15 PSI versus 100,000 for kilopascals, because of the force is greater in a pound and the area is smaller in the square inch versus the square meter. Okay, and then I mentioned 10 meters of water is an atmosphere. 760 millimeters or 76 centimeters, about this much, is also of mercury, is equal to an atmosphere. And why is it 10 meters of water and this much mercury? It's because mercury is about 13.5 times as dense as water. So mercury is very heavy. So if you ever see a jar of mercury, pick it up with both hands because it's going to be really heavy. So, this is equal to 760 millimeters is equal to about 30 inches. I don't know what it is exactly. If you ever watch the news, they give the weather report. They'll say the inches of mercury. An atmosphere is about 30-ish. I think it's. What's an atmosphere in inches of mercury?
The answer is 29.92 inches of mercury.
Okay, there you go. So, I don't think in inches of mercury that much. But then they'll talk about high pressure systems and low pressure systems, that kind of stuff with the news. Anyways, all right, so this is important for the next, why do I care? Why do you care? Because I have to do a unit conversion for the next example. So what is the density of nitrogen gas at 125 Celsius and a pressure of 755 millimeters of mercury? So the density, which we've just covered, is pressure times molecular weight all over RT. Okay, good. You can see that. Okay, good. I got the smaller pen tip on right now. I was just checking. So our pressure then, 755 millimeters of mercury. We got to convert this to atmospheres. So atmosphere over 760 millimeters of mercury. Molecular weight, so nitrogen is 14, nitrogen is 28 grams per mole. I'm getting the 28 grams per mole just by that number times 2. Over R, 0.08206, liter atmosphere over mole Kelvin. Temperature is 398.15 Kelvin. That's 273 plus 125. Put that in our calculator. And this equals 0.855
grams per liter. So let me take a picture. Okay, so one of the dangers of using our calculators are, and one of the most common mistakes I see from students is what's order of operations. What many students will do in this case, you can do one of two things. You can put parentheses around this and then put a multiplications. I guess you can't see that. Let me put it in yellow. Can you see this? I guess you can. So if you saw I had the whole denominator there, you can put the denominator all in parentheses. That will work. But one of the things that I just subconsciously do is I kind of feel like I'm being timed the test. So I put in the fewest keystrokes into a calculator as possible. So because of that, I use the divide key twice. Let's say that if you didn't put that and you put a multiplication sign here, what the calculator would do this number divided by, it would go left to right. This number divided by that number times 28 divided by this number. Then there would be this whole number here. Then it would multiply it by 398. So remember that when you're putting things in your calculator. To do that, to make sure that you have the proper order of operations. If when we're doing these chem quizzes, I do want you to come and bring your calculator and put the numbers in your calculator, because put the numbers in a calculator, that's called a psychomotor skill. So psycho, the brain, motor, doing stuff. So that's actually an important skill to have. And from what I understand from the high schools here, you don't necessarily, some of the people don't ever get those skills, the putting the numbers in the calculator skills. So, and if you put your numbers in the calculator and you get a different answer than me, tell me, like either when I'm going around in class or after class, or even, I guess maybe in the middle of lecture, I don't care. So, because you could be putting them in the calculator incorrectly. And that also is a very common mistake. So, all right, so recap on this one. The new step that, besides the new equation, converting a unit. So you can't see that. Jeez. All right, so this millimeters of mercury, those cancel there, and that's because the unit's atmosphere. So I have to convert the pressure unit. So that's the new thing with this one. And then your answer you get is 0.851 grams per liter. If you look at water, liquid water, this liquid water is 1,000 grams per liter. So not surprisingly, what you learned today in chemistry class is air is much thinner than water. So solids and liquids are also oftentimes referred to as a condensed phase, because solids and liquids tend to have much more matter in them than gases. Gases are also considered, generally speaking, to be very thin, right? So I like to swim, and if I'm underwater and I'm moving my arms like this, if I were to take my arms and go like this, I'd even shoot backwards from the thrust of it, and then I would go forward, going in that way. So if I do this in air, right? I can't even feel a thrust I'm pushing all the air this way. I don't feel any thrust from it, right? So underwater, if I started doing that, I'd be like, like a crayfish, or a crawfish, or whatever you want to call it. I had this argument this weekend about what to properly call the crawfish, crawdad, or anyways. Little lobster, freshwater looking things. That's how they swim. So, yeah, so there is a lot more matter in liquid water than there is in air, not surprisingly, as evidenced here by about a factor of 1,000. So,
Anyways, we got 1 minute left. So, and then that's a wrap. We're done for today. So remember, gas law stuff, not on till the next midterm, so. But you will see it again. And I'll see you Wednesday.